All right. Well, just handed back some homework again. We're locking students out of our class. Welcome. Are you ready for the big last final complete code generation on Thursday? Any questions?
We just have to change or make the generate code methods, right?
Right. So you print out the code and the listing both this time.
And generate code will just be binary.
No.
Well, it will be hex.
Hex for the, oh yeah, yeah.
It will be hex for the loader. So the only formatting requirement is that if you copy and paste from your hex object code, you should be able to copy that, paste it into the object pane of the PEP8 simulator, and load and execute.
Do we need to like return lines at all? Or how do we format that?
Well, you have an option. You can do it either. You can either have the whole thing on one line. If you'll notice the way the PEP8 computer does it, the PEP8 assembler does it, I think it has like 16 bytes on a line, and it just does it, just so that it can be one nice long chunk of. That's a little difficult to do. Or you could do it all on one line, but that's kind of hard to see. What I recommend you do is each instruction have a return at the end of each generated code. Yeah, you can, but if you put a return, make sure you don't have a trailing space after the return or before the return.
Okay.
Because if you do, then the loader won't. The loader is very picky about that.
Oh, I see.
Actually, if you want to see how the loader works, there is. Oh, all right. Let's do this.
Does it?
I wasn't planning on showing you this,
Does
but
it require spaces between bytes?
yeah, let me show you. Yes, it does. In fact, do you remember we wrote some machine language code in the beginning of the semester that required, and that spacing had to be very exact. Here, let me show you. I wasn't planning on doing this, but I might as well. Okay, remember here, this is in chapter 8. This material in chapter 8 is not required, but since we're talking about the loader, do you remember the memory map?
Mm-hmm.
Okay, so this is the memory map of the computer. The globals are up there at the beginning of the application program. The stack starts at FBCF and goes up. The heap starts at the end of the program and goes down. And remember that stuff at the bottom is part of the operating system. And look at what's part of the operating. There's actually two parts of the operating system in PEP8. There is the trap handler that implements the deci, deso, stro instructions, right? And then one of those programs is the loader, because the loader is responsible for taking the object code and putting it in memory starting at address 0000. And you can actually see the PEP8 loader. Okay, so here I'll show you. Here is the beginning of the PEP8. The PEP8 operating system is written in assembly language, right? And you can see it, and if you go to the PEP8 app, in fact, you know how we had those examples, the figures, all the figures and the exercise, the figures in there? You go down to the very last one, and it's the operating system, and you can click on that and copy it in, and it's there. It actually executes. That assembly language program is executing every time you do a trap handler. It also executes whenever you do a load, and whenever you load the program. So this is the buffer part, and here is the system loader. It says we have some documentation here. Data must be in the following format. Each hex number representing a byte must contain exactly 2 characters. Each character must be 0.9, A.F uppercase or A.F lowercase, and must be followed by exactly 1 space. There must be no leading spaces at the beginning of a line, no trailing spaces at the end of a line. The last 2 characters in the file must be lowercase zz, which is used to terminating a sentence by the loader. That's the specification for your loader. Okay, those are the formatting requirements. But look at what it does. It does, it has a load, oh, we don't know indexed addressing. We're just learning indexed addressing. So it uses indexed addressing. It clears the index register out to 0, and then it does some stuff here. And here it is. There's the loader. Look at that, on one page. This is how it gets that, because what is it that you are generating? You are generating ASCII characters, right?
Right.
Are you with me? I mean, they are ASCII characters. They're ASCII characters. So what does this loader have to do?
Convert.
It has to convert. So look at what it's commented all there. Get the first hex character, put the ASCII into lower byte of accumulator if the end of file sentinel is ZZ. So see how it's compare accumulator to Z. Notice there's the sentinel one, okay? And then if the character is less than or equal to 9, assume decimal. So this doesn't do any good error checking to make sure that it's all hex, you know, okay? It just, if the character is less than or equal to 9, we assume it's a decimal, and the right what, Brooke?
Nibble.
Nibble, which is what you're doing, nibbling on your lunch. Oh, that's on posterity for all time now. And the right nibble is the correct digit, else convert the nibble to the correct digit, and then shift left by 4 bits, because, you know, each one of those represents 4 bits. Right? Each hex character represents 4 bits. So it has to do, notice it's ASLA, ASLA, ASLA 4 times. Yeah? And it's doing it, and then save the most significant nibble, get the second hex character, put blah, 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 blah. And then skip the blank, and skip the blank. See, notice on line F, at location FC94, skip the blank or the line feed. That's why there has to be just one blank or one line feed in between. You see what I mean? It skips. You know, it could actually be any character. You could put some garbage character in, weird garbage character in between every pair, and it would just skip it.
Instead of spaces?
Instead of spaces. It doesn't check to make sure it's a space, it just skips it.
Huh.
Do you see what I mean? This is a very simple, the whole idea here is as short and simple as possible with no, you know, nothing fancy. Yeah, no assumptions. I mean, the assumption is that it's in there correct. That it's correctly formatted. Yeah, so anyway, that's it. That's what runs whenever you do the load option. And that's what it will do to your object code. That's how it will load your object code. Okay, well, that's how the loader works. All right. So are there no more questions about the code generation?
Not until I run into trouble with it.
Not until Thursday.
Not until the day it's due. Well, that's
After I've spent hours working on it.
yeah. Okay. All right. Fair enough. All right. Then let's move on. Now, at the end of class last time. Oh, there is one thing I wanted to say about your assignment that I gave back. I noticed that, and I have not mentioned this before, I haven't actually pointed this out before, so I can see why it's been a problem. Let's go, it's on your trace tags when you use call by reference. All right, now, remember here on figure 6.27, this was the first time we did call by reference with global variables. And let's take a look at the function swap, which is a void function, and it has a call by reference R and call by reference S. And order has call by reference X and call by reference Y. Well, I noticed that when you did a call by reference on your homework assignment that you handed in last time, that everyone was using an integer, decimal integer. The convention, and you know, and I kept seeing, why do I have all these negative numbers in the trace? You know, I was running them through the tracer, and I said, why are we having all these big negative numbers? And then it dawned on me, oh yeah, it's because you're not using hex. The convention is, notice here on figure 6.27, how we have R dot equates to 6. And that's the offset on the stack. But look, it's formal parameter. And what do we have here?
2H.
Pound 2H. That's what you should do whenever you have a variable that's called by reference, because it's an address, and and if you display it in hex, you can see, oh, that's this hex address. Like, you know, it makes more sense. And what's really weird about it is that if you do those with D, and the address is way down on the stack, down there at F something, there's a 1 in the sign bit, and it comes out to be it's displayed as a big negative number. Did you notice that when you were tracing, by the way?
I didn't even look at my trace.
Well, no. I mean, look at the trace. Did you don't ever like trace single step through and trace your program? Yeah,
I
but
didn't even think anything of it.
yeah. Well, anyway, the reason that was negative is because you were using D's. I didn't count off or anything for it. But anyway, and also this is going to be the same way with pointers, because pointers are addresses. So whenever we do pointers, we'll also use the hex, the pound 2H. All right, so that was just a little something to be aware of. Yeah,
Exactly right.
Next week's dead week.
I wish we
Yeah.
actually had dead week.
you wish Dead Week were dead.
Yeah.
Yep.
Okay. So now we have. We're going to learn about we only have 2 more data types to learn.
Dynamically allocated.
Yeah, one is arrays and the other one's dynamically allocated variables with pointers. All right, so now, and we were just talking about arrays last time, and I actually posed a question at the end of class last time that then we got off topic.
So we never answered that.
And we never answered that question. So let's go back to this question that I posed.
Oh, okay.
Okay, now look, in stack relative addressing, like here in figure 6.33, with stack relative addressing, we have mem sub sp plus operand specifier. So what happens is you take what the CPU does with stack relative addressing is it takes the content of the stack pointer, which is a register in the CPU, it adds it to the operand specifier, and that addition, that sum, is where it goes to get the operand. And so what happened was that operand specifier is usually the offset, from the stack pointer. Is everybody with me on that? But then we said here, in indexed, it's the same kind of thing. With indexed addressing, you're taking the content of a register and you're adding it to the operand specifier. But this time, instead of taking it from the stack pointer, you're taking it from the index register. Now my question is, why do we do SP plus operand specifier with stack relative? No, sorry. Why do we do, no, that was right. Why do we do SP plus operand specifier in stack relative addressing, but we do operand specifier plus X? We do it the other way around.
I have an idea.
Oh, you have an idea?
Could be wrong. Well, for stack pointer plus operand spec, you're kind of at the stack pointer. That's like going to be the big address number, and you're adding operand spec to it, which will be a smaller number.
Yes.
Could it be that with index, operand specifier is kind of where you're at?
Yes, that's exactly it. What happens is, the second one is, the first one is kind of like your base. It's called, sometimes it's even, in some architectures, it's called the base address, okay? So it's the base, and then the second one is the offset from that. And that's exactly why. With indexed addressing, what is the operand specifier, do you suppose? Yeah, but what do you suppose it is with an array?
Like the very first one of the array?
It's the address of the first byte of the array. And then the index of an array is what? When you say sub 3, that's the fourth one. So it's added on from there. Are you with me?
So index 0 would be just the same thing as operand specifier.
Yes, which is the address of the first byte of the array. Now, does everybody see that? So that answers that question that we left hanging last time. All right? And now, just to give you an example, this next slide shows you the addressing modes of the Intel x86 chip, which is common in most desktop computers now. Now that Apple has switched over, now everybody's using Intel chips on the desktop, right? And these are all very similar, just to show you. I mean, that these are. Do some of these look familiar? Immediate, direct. A register, there's several registers, so you can add one register to another register. You know, that's register addressing, so you can access a bank of registers within the CPU. And then there's this base addressing, and then there's base. What ours corresponds to is like base plus displacement. There's index plus displacement, scaled index plus displacement. The scaled index, you'll see what we have to do in order to do have the same effect as a scaled index. We're going to have to do that in a minute here. And then there's a base index, base scaled index plus displacement, base scaled index plus displacement, and then PC relative. You guys are in computer organization, you recognize that one? How does that one work? Instead of adding the offset to, well, what do you add the offset to? Instead of adding the offset to the stack pointer, or instead of adding the offset to the index register, what do you add it to?
To the program.
The program counter. Wherever the program counter is, you offset it from that, and that's where the operand is. So that's PC relative. PEP8 does not have that addressing mode. But it doesn't have a lot of these, but it's very similar to this whole set of them. All right, so here's indexed addressing. The operand is, you take the operand specifier, which is the first byte of the array, you add the content of the index register, and that's where you go to get the operand. The assembly language ASMB 5-letter is X. And it's pretty simple to see how we do it with how we implement global arrays, or how the compiler translates global arrays using indexed addressing. Okay, so here's the recipe for how to translate global arrays. First of all, how do you always allocate a global variable? With dot block. Only this time, how big is our dot block going to have to be?
The number of bytes in the...
Yeah, it depends on if we have like an array of integers, each integer is how many bytes? 2. So if we have an array of integers, suppose we have an array of like 4 integers, then how many bytes are we going to have to allocate? 8. Okay, so we still do dot block, yeah? And now, here's the question though. How do we access element v sub I? See, here, let's do a little picture.
With index addressing?
Yeah. See, if this is our array v, and okay, then this would be v sub 0. But the thing of it is that if this is an array of integers, this says let's assume that it's integers. Then the first integer is going to be here, and the second integer is going to be here, and the third integer is going to be here, right? So this would be v sub 0, this would be where sub 1 is, and this is going to be where sub 2 is. So, well, let's do one more. And this is going to be where sub 3 is. But now I ask you, where is v sub 3? What do we have to add? What do we have to add to this to get to the third one?
6.
We have to add 6, right? So from here to here, it's a 6-byte offset. Does everybody see what I mean? There's a 6-byte offset to get to
3.
To v sub 3. So to get to v sub I, what is it? You got to get I times 2. Are you with me? I times 2 has to be in the index register. But now, of course, this is just for integers. If it's an array, if it's an ASCII of characters, then you don't have to do, because each character is 1 byte. Are you with me? So do you see what the recipe is? Why we have the recipe like it is? to access element v sub I, you load I into the index register, you multiply by the number of bytes per cell. In this case, it would be 2. And then we use indexed addressing, having the address of the first byte be the operand specifier. Is everybody clear on that? All right. So, with that concept in mind, let's see if we can do this. Here is our first little program that doesn't have any...
Branch to main.
Okay.
No function.
No functions. We're just going to see how arrays work. Okay. So we have int vector, is that 4? Okay, so let's just draw a little picture.
Branch to main.
Yeah, only
What's the
int
first
vector
thing?
4, so it's going to be like this. So this is going to be, this is vector 0, 1, 2, 3, right? And then int j, so j will be here.
Is the whole dot block thing the reason why we always have to declare the size for our arrays?
Yes,
Yeah.
yes, because it's in a fixed location in memory.
Yeah.
Yeah. All right, so somebody said branch to main, so let's,
Something.
okay, branch to main. But now here's my question, what about vector?
Call it vector, do a symbol.
Call it vector,
Oh.
symbol,
Dot
and
block.
dot block, but now what?
8.
Dot block 8. But now the question is, global array,
2D.
No.
well, it's going to be pound 2D.
Pound 2D, pound 2D, pound 2D.
No. Fortunately, there's a, now comes our trace tag.
All.
No. How many cells?
4.
For
Oh, cool.
pound 2D for,
See?
D.
Oh, it's integer.
oh shoot. No.
5.
Pound 2D for A.
A.
Or
Array.
Array.
4 cell array.
Okay.
2 byte decimal, 4 cell array.
Okay.
All right? And guess what will happen
It'll do it.
on your tracer?
It'll be over.
It'll be just like this.
Cool.
There you
Okay, and now what?
Symbol J.
J
Dot block 2.
dot block 2,
go. Pound 2D.
global 3, pound 2D. All right? Is everybody good so far?
Do.
Okay, and now what's, now here we have main.
Load 0.
No locals or anything, right? So 4J gets 0. So
Load 0. Immediate.
load accumulator 0 immediate.
Store J direct.
Store accumulator J direct because these are globals.
4.
Say it again.
Yeah,
So
symbol
symbol
4, right?
4, I guess. Yeah.
Oh, 4.
Actually, we need to have.
Well, this is the,
Because
oh,
we'll
this is
add
the
it- we'll add
initialization.
it,
Is this
so-
the test?
This will be the test.
Okay, so so you want to do,
So,
you want to optimize or no?
yeah.
All we have to do
compare
is-
accumulator.
We've loaded here, and we'll load again at the end of.
We'll load again at the end, so
So we can just-
let's just do, so compare accumulator what?
4.
4 immediate
branch.
Branch if.
Greater than equal to.
branch greater than or equal to, that must be less than up there, huh?
Yeah. And for 1. And we should also name that symbol.
We
for
should
1.
name this one 4-1 because there's more than one 4. Okay?
Now, this.
Now what are we doing?
Deci.
Deci.
Deci, oh, not yet.
What?
What?
Ha ha! Yeah.
We have to go to the location.
Because what are we DESIing in, what are we DESIing into?
They're right.
What are we inputting into? Yeah, but which one?
So do we have to load
Sub
load
I.
X vector?
How does indexed addressing work?
Do we have to get to that location? We have to add the.
We had,
We're gonna use indexed addressing, right?
Yeah.
But in order to use indexed addressing, what has to be in the index
we have to
register?
load J.
Load what?
J, which is I. In this case.
J-
Load the base,
what?
right?
I think we have to load vector, the
I thought we
address of
loaded
vector.
vector.
Maybe not, wait.
I think
We have to
that's what I was
load-
thinking.
We have to load.
No, think about, no, you should be able to think through this. Let's, if you can work through this, then that'll be really
Don't
good.
we want to add the first?
It's the operand spec.
No, we
X.
do load J.
Yeah, you want to load the index?
Into where?
Index register.
How do we do that?
Load
LDX.
X,
LDX. So we, LDX,
J,
J.
J,
immediate?
immediate.
Perfect.
Are you with me?
Yeah. Wait. It's direct.
It is direct. Did I say immediate? Or
Yeah,
did
you
somebody
did.
else say immediate?
Okay.
Okay.
Now we can
No, we
designate
can do that.
vector.
No.
No, we have to multiply J by the number.
We have to multiply J by the number of bytes in each cell.
So ASRX.
R or L?
Left, yeah, left. Arithmetic shift left.
Okay, so ASLX.
Shifts.
Are you with me, sports fans?
Yes.
Okay, so that's the 2 per, okay. And now what?
Now we can desi.
And what do we desi?
Desi vector X.
Desi
Indexed.
vector indexed addressing.
Yay.
Now, does everybody see how that worked? Because what's going to happen is vector is going to be the operand specifier. That's going to add 2 times whatever the value of J is, which is going to get it to the right location, and it's going to be desi from there.
Perfect. And now we,
Now we have to add 1 J.
So how do we do that?
Wait, do we? Because we multiplied it.
Well, we better load it.
Later.
Well, no, I know, but it's been modified.
Load
So let's load
Load
no, not an accumulator. Oh, well,
Yes.
Yeah,
right now it's.
we
not
have
doing
to. 'Cause don't have
you know what we should do?
Can we just add 2?
No.
Add 2.
We should just be keeping this J,
in the,
we should just be keeping this J in the index register.
instead of the accumulator.
Yeah.
Okay.
I mean, why not?
But what,
But
don't
we-
you double it
But
and then
we
you?
doubled it.
Yeah, but we will,
Can you?
yeah, it's true, we will double it here, but we'll just reload it.
Can you add X?
Well, okay, we'll just keep it in here.
Oh, I see what you mean. Okay.
You can add X as opposed to add.
Oh, yeah.
Yeah.
Yeah, that's that R, you know, it has that R field?
It's either
Oh,
A or
okay.
X.
Yeah. Okay, we'll just do it this way. I think on the slide we'll see it's slightly different, but okay, so what do we have here? Load accumulator, J,
Correct.
direct,
Add accumulator.
add accumulator, 1, immediate,
Branch to 4-1.
and,
Branch to forward.
right. Branch to 4-1. And then this is in 4-1.
Mhm.
Yeah, let's start a new column.
New.
Okay, so over here,
Can you put 2 symbols on the same line?
no. You cannot put 2 symbols on the same line.
Does that
Okay.
make sense?
Load
You might as
accumulator
well
J.
just reference the 1 symbol.
So say it again, load accumulator,
3. Sorry, load accumulator 3.
load accumulator 3? What's 3? Oh, because we're starting, oh, okay.
We go down.
Oh, I see.
Store accumulator J.
Store accumulator J,
Direct.
direct,
Branch if less than
branch LT
0.
to end,
To N42.
Oh, we are comparing.
Yeah.
okay?
We need a 4-2 symbol in front of the branch plus them.
Not in front of this, for the next one, right?
Right here.
No,
No,
we have to do the
because we'd
check.
have to test.
The test is the branch.
Why don't we just use N41 as where we want to go back
You could
to?
go back up to that, but you don't have to go all the way to the load because we're adding.
Oh, no, that's right, we don't want to load.
So yeah, the 4-2.
Okay, I'm not, I don't have the code in front of me. I'm not sure.
14 needs to be at the branch,
Really?
because that's the check. We need to come back up. to
That's the
check.
for loop.
All right, I'll take your word for it.
Yeah.
Okay.
There's 4-2
And then Deso?
character. Oh, yeah, that's so.
Yeah.
Deso,
Yep.
Yeah.
J. Direct.
J, direct,
Caro.
Space.
Space. Immediate.
immediate,
Now we
Might be
load
some stuff.
index register.
Load X.
load X,
J.
J, direct, A, S, L, X,
And then deck go.
Deso.
Vector. X.
That makes sense.
Yeah, doesn't that make sense? You just, yeah, everything, once you sort of get the whole concept of addressing modes and what's a value and what's an address and how everything's laid out on the memory map, all right?
Load accumulator.
You don't have to memorize this stuff. Because you can just understand it, you don't have to memorize it.
Oh, character out and line.
And say it again,
Character out and line.
dash in, immediate,
Load accumulator J. Direct. Sub accumulator.
sub-accumulator,
1.
Immediate.
1, immediate,
Branch 2, 4-2. BR.
we don't ever store back to J?
That's what I'm saying. Do we need to load it again?
Yeah, we need to store back to J right now.
I say, do we need to store back to J before we,
Or we can just put 4-2 up 1. The symbol for 4-2, we can put it up 1 line.
oh, yeah, well, we're really,
I don't think we need to store back to J because we're not changing the accumulator.
you know what, I
Because we're using the
think,
index register.
yeah, you know, actually, I think the code here might be a little bit different.
But we do
They'll
just
store back to
output
J if you're using the index register the whole time.
We just, oh.
But if we aren't storing
We
it-
never changed the accumulator, so we changed the index register.
No, we decimal output J
Yeah,
though.
we need, J needs to be
So it
different.
needs to be changed for that reason.
So if we just lift,
Yeah.
put 4-2, the symbol for 4-2 up.
Yeah, so I think, so we're saying we need to store accumulator J here, right?
Well, we can do it if we, okay.
You do that?
Just put 4-2 up 1 line.
Yeah, that's what I was gonna say.
Store accumulator J.
Output J.
Actually, not,
Should we do that over there?
yeah, I think we need to, don't we?
Yeah.
If our analysis here is the same as over here.
Yeah.
Store accumulator J,
Direct.
direct, and then branch to what?
4-2.
4-2.
You're right.
And then N42 would be the next line.
etc.
Stop.
Yeah.
So right there, you just need to lift up.
And so here, are we saying that here we need to,
Store.
right here? Store accumulator J, direct, and then branch.
Well, I don't know if we need it in the first 4. We
do.
never output it.
Yeah.
Oh, we never output it.
But if we
We see
reload it
into
again,
it.
doesn't it go back to what it was before? We changed it? So wouldn't it stay on the same value every time?
Yeah, she's right. Because we load X from J,
Yeah.
and if it never changed, then.
Mm-hmm.
Yeah.
We have
But we
Okay,
just
well,
compare
there's-
the accumulator at the 4-1.
Yeah, okay, but then you're loading X at J.
And if J's not going up at all, it'll never.
It'll never
Okay,
change. It'd
that
be the
makes
same
sense.
every time.
Okay.
Okay.
Are we good here?
Mhm.
Yeah.
Yeah.
Okay, now, so here is how the, did we get our
Block 2.
pound 2 D4A? 2-byte decimal, 4-cell array. That's how you say that. And then a global variable, pound 2D. And now here, I think what we did, I think what I did here,
Yeah, it's all.
I think it's all with the index register, but let's look at this code and see if how it compares to ours otherwise. So load X 0 immediate, that's the 4J gets 0, store X J direct. Compare X, so we did the optimization there, right? For immediate branch of greater than equal to N41. And then ASL X deci vector x.
I have a question.
Yeah.
How come we have an accumulator?
To do,
Anything we can
Any-
do with an accumulator, we can do with an index register, right?
Well,
oh yeah, well, because it's for doing stuff like this. So the question was, why do we even, over here? So the question is, why do we even have an accumulator at all? It's because what if you want to do something like this? V sub I plus 3. Or what if you want to have V sub I plus, what if I want to have V sub I plus
Hi.
W sub j? Well, you want to have an index register for this, and get that into the accumulator, and then an index register for this, get that, and then index register for that, and add that to what's in the accumulator. In fact, if anything,
you need
PEP 8 is lacking in registers, and it doesn't have too many. So, because in a real, those of you who are in computer organization, we're studying the MIPS computer, we've got 32. 32 registers, and so what they do is they keep all the variables. They assign, they have a register allocation algorithm that assigns each register to be a different local variable, and anyway, it's a different. But so anyway, this
Can we
is.
do all algorithms with just 2 registers? It just takes a lot longer.
Yes, this.
So you can do
It's-
everything with a 4.
Minimum?
Yeah. As long as you have infinite memory, this and just about any other thing that's similar to this is Turing, is equivalent to a Turing machine.
Turing equivalent.
Turing equivalent. All right. Okay, but wait. Let's. So what? How did this one? How is this code compared to ours?
They don't use the
It's
accumulator.
identical except for we use.
But I mean, did we optimize the same way up here?
Yes.
Okay. And what about this?
Same. It's just they use the index register.
It is just use the index register. All right. Are we good? So here's a picture. And I could show you a demo,
But I believe.
but you can, we've done lots of demos before. And you can do this, bring it up on the demo, and you can see how it works. All right. Now, the other thing. Okay, so that's how we do arrays with global variables. Next question is, how do you do arrays with local variables? Well, now think about it. Here, let's take a look at this picture right here and see what would happen if this were, if these were local.
They'd be on the stack.
They'd be on the runtime stack. So now what's going to happen is, see, this picture would look like this. It would look like this. First of all, we'd have these 4 here.
4.
So this would be vector 0, 1, 2, 3.
In that order?
Like that, yeah.
It pushes 0.
Oh, yeah, oh, yes. By the way this works is, as you go up in the index, you go to the next cell in the array.
So you actually push.
Are you with
the
me?
last cell first.
Well, no, you do you sub SP the whole amount.
same thing.
Yeah, you sub SP the whole thing. And then what would
And the
happen
vector is stack relative 0.
and then what would happen is J would be here. All right, and then instead of vector being the address of the first cell in the array, it would be the what? See, SP would be here.
The
It would be
displacement
dot
on the stack
equate.
point.
It would be the displacement from the top of
stack point.
from the top of the stack frame
To the first cell.
to the first cell of the array on the stack. Are you with me? We good? So in this case, what would J be?
equate 0.
J would dot equate to 0 because it's 0 offset from where the stack pointer is going to be at the top of the frame, and vector
Dot equate 2.
would dot equate. Actually,
Okay.
this would dot equate 0, this would dot equate 2, because it's, you know, the offset here.
So it's similar to how we did local variables with call by reference.
Exactly.
It's a similar idea.
Yeah. Yeah. And now what kind of an addressing mode do we need?
SX. Stack index.
So we need an addressing mode that will do this for us. And that is the SX, stack indexed addressing. And is all it does, well, here, what does it do? What, according to this recipe, what is the operand? You take whatever is in the stack pointer, whatever is in the stack pointer. So now the stack pointer, now you see why we put the stack pointer first? That's kind of like the base of where we are.
Yeah.
But then the operand specifier is the offset to the first byte.
To the first byte. And
Are you with
add
me?
the index.
And then you add the index, however many down bytes you go, and still that, with it, you got to make sure you do the ASL2 if it's an array of integers, because each integer is 2 bytes long.
And then stack index deferred just gets what's there.
Well, yeah, yeah, stack index deferred, that's the last, that's the penultimate one we will learn.
No.
This is
Not the
this is the
anti-penultimate?
answer.
No, this is the this is the anti-penultimate
Oh, good.
addressing mode that we will learn. We actually used it in a sentence. And the assembly language ASMB 5 letters SX. And so here's the recipe for local arrays. All right? So what you do is you allocate the total number of bytes of V with sub SP, and we deallocate with that SP just like before. And to access element V sub I, we load I into the index register, multiply by the number of bytes per cell, and we use stack indexed addressing, SX. Is everybody good? Oh, rats, I should not have erased all my code.
Whoops.
Is this the exact same one?
Yes.
This is the exact same one, only it's with locals.
We need an undo button.
We can look at the second loop and understand.
Yeah,
everything.
yeah, okay. Well, okay, so we'll start, wait, is this, okay, we can branch to main here, right?
Okay. We could just do the second half.
Actually,
we
isn't
still have
there,
that.
is there such thing as branch to main? Did you just go straight to main?
We-
Well, you know, because these are not generating code, you actually could dispense with your branch to main, but we just put it in. It's really branching to the very next instruction, and it's superfluous. But
So it takes an extra instruction.
it takes an extra instruction that's not needed, but rather than have to think about that every time, I just always branch to main.
Okay.
But you're right, it is, in this case, it could be superfluous.
Okay.
That has come up before and you didn't notice it till now.
The dot box we don't need.
Well, if you don't have a dot, if you have a dot block, then you do have to branch to main. Okay, so here's main. Okay, sports fans. Oh, wait a minute, what about our, this is what? Local,
2D.
pound 2D. Pound 2D, and this is going to be a local.
2D4A.
Pound 2D4A. Oh shucks, I think this is going to be very,
Very similar.
yeah. This time let's use the index register.
Okay.
Okay.
So what's the first thing we got to do?
So,
Load index.
Load X,
Load X.
Load X,
0,
0,
Immediate.
immediate,
Store.
store
X.
X,
store X.
J.
stack relative.
Stack relative.
Well, do we?
Wait.
Oh, we missed something, we missed something. Yeah, they're locals. We all realized at the same time. So sub SP,
Code 10.
10,
Immediate.
Do we sub
Immediate.
SP twice? Once for J, once for vector. Like, well, is that
no,
what-
no,
is
no,
that
we
what
can,
we'll
no,
do?
we can do it like this.
Okay.
And then we just have to.
And what we're doing is we are allocating,
J goes first, right?
No, it's in the order that we get
Oh, we're
them,
doing
right?
vector
So
first.
pound vector,
Okay.
pound j.
So allocate pound vector, pound j. Are you with me?
Now we can load up.
Now we can load x. What?
0,
0,
I.
immediate,
store,
Store X.
J direct, or S.
S.
j, stack relative,
compare,
compare accumulator,
x. Wait, it's not
Eh.
in the accumulator
Rather-
though.
Isn't it 4?
Oh.
But it's not in the accumulator.
oh, compare x, CPX,
Okay.
There you go.
4.
Maybe.
4,
Immediate.
immediate,
Branch if
Branch
greater than or
if-
equal to.
Greater
branch if greater than or equal to,
than. And 4, 1.
and 4, 1.
We need to put our and 4-1 thing up there.
Where do you want to put it?
Right there.
Right here? Okay.
Okay, so now we
Now-
load x. Oh, it's already loaded though.
Do you want to optimize?
Yep.
Okay.
Now we are arithmetic shift
Left.
left
ASL X.
Yeah.
And now,
Deci.
deci,
Yeah.
decimal input, what?
Vector. SX.
SX. And then what?
Then we
Add 1 to J.
wait, no, we have to load x with j.
Because J's different.
Load X, yeah, J's been modified, so load X, J,
Stack.
S,
Then we
Add X.
add X,
1 immediate,
1 immediate,
load x. I mean, sorry, store x.
store X.
J stack
J.
over.
Branch to 4, 1.
4, 1.
Now,
Now we get back to.
and 4.
Yeah, and, yeah, and the rest,
Yeah,
the rest will be similar. Now, let's see if we, how we did. All right, so check us out. Does this,
And we just have to add SP at the end of the whole thing.
oh, right, at the end of the whole thing. Does that, did we do it?
Uh-huh.
And this, oh, how about this allocating, did we allocate the right order here?
Yes.
Yes. And you deallocate in the reverse, right?
Yeah, you deallocate, yeah, I've noticed that, unfortunately, the debugger, the program doesn't catch that at runtime when you,
It just does it?
it, oh, no,
It does it all at the same time, no matter what.
well, yeah, as long as the total is correct.
Okay.
Is it by the number of bytes?
It does it by the number of bytes. I've thought about putting that in there and making you do it in the opposite order, making you have your trace tags in the opposite order, because that's the way I like to do it for documentation, you know. But, anyway. Yeah, so probably on here it says deallocate pound j pound vector. Is that what it says here? Here, right? And then here's the picture. Okay? All right then, that's the story about indexed addressing and local and global arrays. And on Thursday, you'll probably have some more questions about code generation. All right, see you next time.